SwayamPrabha. Digital India. Educated India.
So welcome to lecture number 16 of the Statistical Thermodynamics course for engineers. So previously we have seen the steady state version of the Schrodinger's wave equation. In this case, we are going to now write the first multi-particle analysis using the Schrodinger's wave equation. So by multi-particle analysis, we mean that there are n independent particles. Okay, this is multi-particle. So previously we looked at single particle. Remember the previous forms, whatever we did, were all corresponded to the single particle. For the single particle, this was the steady state wave function. So for multi-particle, because these particles are independent in nature, independent particles, okay, the multi-particle analysis will be minus H2 summation I equal to 1 mi square is equal to H bar. So these are independent particles, so they have, so I corresponds to the ith particle. So if we apply the steady state at steady state wave function, what happens is minus H2 equal to 1 to n so that is the steady state using the steady state Schrodinger's wave equation. So this is the total expression that you can write, that H bar is H bar for particle 1 plus H hat for particle 2, therefore H hat for n. It's basically the summation of all H bars, H hats, sum over I. So H I, okay, only coordinates about the ith particle, only is concerned about ith. Okay, so for ith particle, okay, H bar I psi I is equal to EI psi I. This is for the ith particle only. Okay, but remember these particles are all are independent, mutually independent, right? So that is for the ith particle. Now the wave functions, if you write it, psi r should be now psi r1, psi r2, psi rn. That is because since n particles are independent. Got it? So n particles are independent. So how do you write down the final expression? Final expression will be I equal to 1 to n HI. First expression, then of course it's a multiplicative, j equal to 1 to n I j, okay, is equal to okay. So we already know that only effect. So you can see from this particular expression that this is the total expression, because h, just note here, h, for example, k contains no coordinates, other than those, contains no coordinates other than those for the kth particle. Okay. So the only term it affects while operating, the only term it affects on the when operating on the total wave function, the total wave function is I R K. Okay, so in other words, we can write H K over J I J is equal to, now look at this carefully, J is not equal to K, psi R J, okay, put it in a single bracket, another K psi is equal to K into. All right. So we have seen. So this is what it is. So you can work this out independently as well. So this actually, states the full function. So substituting all of this, you can kind of you can write another expression equal to 1 to n ERE. On this wave function is equal to psi. So that also can be done. And the energy is the sum total of I equal to 1 to n of EI. All right. So this is, for example, is applicable for dilute system or dilute systems. Okay. Like ideal gas is one example of a dilute system. Okay. So let's do a very quick recap that you have a system of, if you have a multi-particle system, which is composed of n independent particles. Okay. So if you look at that kind of an expression, and if you just as a recap, if you look at the total Schrodinger's wave equation, then for a single particle, we wrote it like that. This was the time dependent. So 2n psi r comma t plus dr psi r t equal to I h bar psi r comma d by dt. So this was a single particle. When you write it for a multi-particle system, this becomes simply I, and then there is a summation that comes into the picture for I equal to 1 to n, right? Because now this is applicable. This is the individual, for the individual particles, right? So at steady state, the steady state version of this then becomes minus h squared by 2m. Again, you sum it over 1 to n, right? And 1 over mi. Now it becomes mi. Okay, so the previous one, as you saw, was the mi comes because it is the individual particle mass. So this was psi plus v psi is equal to. So this was what we wrote in the steady state version. So this was the steady state version. Okay. So now you can also now see that the Hamiltonian operator now can be separated into a number of terms, which is exactly what we did. The Hamiltonian operator was now separated into a bunch of terms, which is what we did. Okay, so here we say that Hi is only concerned about the ith particle. It is only contains the coordinates of the ith particle. Therefore, based on this, okay, consequently, the operator Hi can be only used to obtain the wave function psi Ri. Okay, so and this gives rise for the ith particle. This is the expression. For the overall wave function, that means the global wave function, which is psi r, okay, therefore must satisfy, h psi r is equal to, this should be satisfied. So the overall wave function should satisfy this particular expression. So for independent particles, the wave function becomes something like that. Okay, because it's a multiplicative of multiple particles. So this single particle wave functions are written as this psi r1, r2, and r3. So now, if we now substitute this particular expression as well as this particular expression, okay, these two, if you substitute in this expression, this guy here. Okay, you get this. Right. Get this. Okay, all right. And however, then we argue that HK contains no coordinates other than those for the particle. So the only term that it affects is psi RK. So therefore, you can hence you can write it in a slightly modified version like this, and then it follows all the other terms that we did. Okay, so this gives for a multi-particle analysis what should be the procedure. Now we are going to do particle in a box. So what is particle in a box? The particle in a box represents the simplest quantum mechanical. It represents simplest QM problem. Okay. Moreover, it also demonstrates many interesting effects of quantization. The solution is also important because it predicts the allowed energy levels for the translational mode. So it basically predicts the allowed energy levels for the translational mode. Okay, of any atom or molecule. Molecule. Okay. So this is important because it represents a very simple problem, but it also predicts that how quantization happens. We will see that shortly. And it also predicts the allowed energy levels, what is the concept of microstates and macrostates here. So all these things will come in very handy when we actually do this particular problem. Okay, so for doing this, let us look at cuboidal box, cubical box. So something like this. This is a box, a cubical box of length L. So the particle, if this is a particle, assume that this is the guy, it can go anywhere in the box. Okay, it can go anywhere in the box, anywhere within this space. Okay, so it can go, the particle can go anywhere in box. There is no restriction on the particles where it can go. Okay, let us assume that V is equal to 0, okay, inside the box. Makes things easier. And V goes to infinity outside the box. Outside the box. Okay, so this actually represents a potential well, right? So the particle cannot go outside. It's like a barrier. Okay, so this is used to prevent particle from exiting the box, from going outside box. Okay. So it essentially also translates to the psi into complex conjugate is equal to 0 outside the box. That is because if it represents probability, then there is no chance that the particle can be outside the box. It's an improbable event. It's 0 outside the box. We also assume psi equal to 0 outside the box. Okay, so this is the probability being equal to 0, as we know that this represents a PDF position of the particle, but so this is 0 outside the box. So if we now assume the steady state equation or the Schrodinger's steady state equation, okay, what we will get, there are 3 coordinates, remember, because this is a cuboidal system. So this should have a x, y, z, x, y system, right? Okay, so this is minus h squared by 2n. And it's square. Okay, so this is the steady state version of the Schrodinger's wave equation. Now this equation, of course, this is a 3-dimensional system now. So what are the boundary conditions? Because this is a partial differential equation, as we can see. But psi 0 y z, that means that x equal to 0, equal to psi x 0 z is equal to psi x y 0 is equal to 0. Got it. And after a length L, okay, that is also equal to 0. Okay, and x, y, z, this is equal to psi 1 x plus psi 2 y to psi 3 z, because each of the 3 directions are independent with respect to each other, right? So this is at one corner, this is at the other corner. So the probability is 0 anywhere from those corners, and it has a finite probability inside the box, right? Inside the cubical box, and the total probability is given as a multiplicative of these 3 terms, which corresponds to the different directions, right? So as we know that the particle in a box is very important because it will allow us to get the energy levels and the quantum numbers for the translational mode. Okay. So let us see how this works. So for each coordinate, okay, we can say psi I, and we are dropping the xy because this is assumed that this is space dependent only. X is 1 I, it's 2m h bar squared, I is equal to 0, I equal to 1, 2, 3, E equal to E1, that's E2, that's E3. Okay. E1 is equal to E2 plus E3. Right. Okay. So the solution for this particular problem, it becomes psi I is equal to A sine 2m EI squared B 2m EI h bar squared. Okay, so this is one of the solution becomes, so the boundary conditions II0 is equal to 0, IIL is equal to 0. Those are two extremes. So this psi I equal to 0 leads to B equal to 0, right? Psi I is equal to 0 and xi equal to 0, right? So this term, it becomes 0, this term becomes 1, so B equal to 0. Okay. And psi I L equal to 0 leads to A sine, put it as 2EI h bar squared into L is equal to 0. Since A cannot be equal to 0, so this would mean A cannot, then it becomes a trivial. If A equal to 0, then psi is equal to 0, so that's a trivial solution. So this becomes 2m EI h bar squared is equal to 0. Therefore, 2m II squared half into L is equal to NI I, and NI is equal to 1, 2, 3, right? Okay. So this being equal to 0 proves this is the point. This we are familiar with. There is already quantization that you see coming right over there. Okay. Now from 0 to L, psi I star I dx implies, if this is, we are integrating the xi, this is a square 0 to L is sine square NI divided by L dx is equal to 1. Right? That should be equal to 1 because the total probability when you integrate it should be equal to 1. So this gives you A is equal to 2 by L into half. Therefore, psi I becomes 2 by L sine NI I xi divided by L. All right. Okay. And EI therefore becomes h square NI square divided by 8m L square. That is the particle mass. All right. So these two are two vitally important. So you have found out the wave function in the ith coordinate system, in the ith direction, and you have found out the energy in the ith direction also. So the overall wave function, now that we know overall wave function, which is written as psi, is basically multiplicative of all these sine n1 by x1. x1 is like your x, sine n2 by x2 by L, multiplied by sine n3 by x3 L. So this is the total wave function, okay, which involves now three coordinates. So it involves three coordinates, x1, x2, x3. So x1, x2, x3 are three coordinate systems. Three coordinate systems. Okay. And okay, n1, n2, n3 are three distinct numbers that we are dealing with. Okay. Three distinct numbers of three degrees of freedom, also you can say. 3 degrees of freedom, and they have integer values. So you can see readily that there is a total. So the total translational energy is therefore E1, E2 plus E3, which is basically the h squared by 8mL squared summation of NI squared. Something like that, which is basically 8. So basically h squared divided by 8m, leaving the volume 2 by 3rd, n1 squared plus n2 squared plus n3 squared, where n1, n2, n3, and v is equal to L cube, which is basically the volume. So these n's, therefore, n1, n2, n3, are called translational quantum numbers. Translational quantum numbers, which is also connected to something like the degree of freedom of the system. Okay, so this is rather interesting. So this is how we found out. This is a pretty straightforward process. Okay, so these are the translational quantum numbers. So the equation is most significant. So because there will be multiple interpretations of this system, because we saw that the energy was quantized, and we can make 5 observations on this, which we'll cover in the next class, based on this analysis. It's a simple analysis, but it has got some profound effect that what is actually meant by doing this. Okay, because we have got 3 translational quantum numbers readily popping out of this particular context. So thank you. We will see you in the next class.